All right, so for this next lesson, we're going to be talking about the formal definition of the definite integral and how to do those problems. So the first thing that we're going to look at is, let's say we want to find the area bounded by f of x equals 2x squared plus 3x minus 1. And the x-axis from x equals 1 to x equals 3, let's say. Okay? Okay, so the first thing that I'm going to do is my little side work, and I'll put that in blue over here. So first of all, we have what a is equal to. Well, that's just 1. What b is equal to, well, that's just 3. What f of x is, well, they give us that, 2x squared plus 3x minus 1. Then we talk about delta x. Remember, this is just b minus a over n. So in this case, it's going to be 3 minus 1 over n, also known as 2 over n. Next, we want to talk about x sub I. Remember that x sub I is always equal to a plus delta x times I. So in this case, x sub I is equal to my a value, which is 1, plus delta x, which is 2 over n, times I. So the way that I would write it is 1 plus 2i over n. And then f of x sub I is the next thing that we're going to do. And I'm actually going to do that, not over here, but I'm going to give myself more space to work with this. So I'm going to go over here that f of x sub I is equal to 2 times something squared plus 3 times something minus 1. And I say something because this has x and x, but now instead of only putting in an x into the function, I'm doing x sub I, which is equal to this thing. So that's what I'm going to plug in right here and right here. So now let me simplify this a little bit. So first of all, this is 2 times quantity, 1 plus, what is that, 4i over n plus 4i squared over n squared, plus, let me distribute the 3, and then that minus 1, and now let me distribute that 2, so this is going to be 2 plus 8i over n plus 8i squared over n squared, plus 3 plus 6i over n minus 1. So really, when everything is said and done, let me collect like terms here. So I'm going to have 8i squared over n squared plus 14i over n, and then plus 4. Okay, so that is f of x sub I. So now, let me scroll down here. So that was all in blue. That was just to get my different values. But now I know that the integral from 1 to 3 of my function, which was this 2x squared plus 3x minus 1, I'm just going to call it f of x dx, is really equal to the limit as n approaches infinity of the summation as I goes from 1 to n of f of x sub I, which is 8i squared over n squared plus 14i over n plus 4 times delta x. Remember, my delta x was just 2 over n, like that. Okay? So now this is equal to the limit as n approaches infinity of, so the first thing I'm going to do is I'm going to bring this guy outside. So that puts me at 2 over n times the summation as I goes from 1 to n of 8i squared over n squared plus 14i over n plus 4. Okay, so that's the first thing that I do. The next thing I'm going to do is apply that summation to every term inside and factor out of the summation everything that is not an I term. So this is equal to the limit as n approaches infinity of 2 over n times, so here we go. When I apply the summation to that first term, I get 8 over n squared times the summation as I goes from 1 to n of I squared, plus 14 over n times the summation as I goes from 1 to n of I. And then I'm going to leave this one as the summation as I goes from 1 to n of just 4, because there are no i's in that one, and so I'm just going to treat that as that constant formula for the summation that we talked about earlier. So now this is equal to the limit as n approaches infinity of 2 over n times. So here I'm just replacing that and this using the formulas that we talked about in class. And so this is going to be 8 over n squared times. Remember, I squared was the n times 2n, n times n plus 1 times 2n plus 1. I did it in that order, so I don't want to confuse you. All over 6. And then plus 14 over n times, this was just n times n plus 1 over 2. And then this one over here is just going to be 4n. Okay, so now I'm going to distribute through by this 2 over n. So this leaves me with the limit as n approaches infinity of, and again I'm going to put my constant terms over each other and then my variable terms over each other. So here I'm going to get, okay, 2 times 8 is 16 over 6 times, and now this is going to be the n times n plus 1 times 2n plus 1 all over n cubed, right? Because I multiply that n times n squared there. So plus, so here we go, that's going to be 2 times 14, which is 28 over 2 times n plus 1 all over n squared, again because I multiplied through by that 2 over n, so that n in the denominator multiplies with that n in the denominator to give me n squared. And then plus, now that just gives me 8, right? Because 4n times 2 over n, the n's cancel out and you're just left with 8. So I'm going to simplify a little bit here. So 2 goes into that 8 times, 2 goes into that 3 times, 2 goes into that 14 times, and 2 goes into that 1 time. And so now when I apply the limit, I get, so looking at, let me choose a highlighter. So looking at this right there, that is going to go to 2. So just what is, when I take the limit as n approaches infinity of that whole thing, I'm going to get that the numerator has a degree of 3 and the denominator has a degree of 3, so it's going to be leading coefficient over leading coefficient. And for the numerator, it's going to be 2n cubed plus something, right? And the denominator is just n cubed, so that whole thing is 2. So times 8 thirds gives me 16 thirds plus. So now when I apply the limit to the second term, this right here is just going to be 1. And I get that because I have n squared plus n all over n squared. And so when I take the limit as n approaches infinity, the degrees are the same, they're both 2, and the leading coefficients are both 1, so it's going to be 1 over 1, which is just 1. You multiply that by 14 over 1 to get 14. And then here, when I take the limit as n approaches infinity of just 8, I just get 8 back. So this together, right, so that's 22. That right there, this guy is also known as 5 1/3. So this whole thing is 27 1/3. Okay? So that's what we got. And that is using the formal definition of the definite integral to evaluate an area problem, which we know is just this definite integral. All right? Hope that helps.